Replacing a single broken spoke on a bicycle's wheel is really not rocket science. It will only take you about 3 minutes of your time to actually mount the spoke into the wheel. In this video I'll show you what's involved as a big picture in just getting to this 3 minutes of spoke replacement. I'll focus on showing you how the spoke placement is done, focusing on the correct geometry or placing the spoke or lacing the spoke correctly into the wheel. I'll also have some notes on spoke quality or metallurgy or metal bending, if you will, and that's gonna be the focus of my video. I will also show you what tools I need, using this wheel as an example for getting this job done. I will in passing just mention some of the differences in terms of wheel geometry. Your wheel might be different and you might need additional or fewer tools or different tools than what I need. So I'm not going to pull off the cassette set from the hub. There are two reasons for it. One, the spoke is missing from the other side of the hub flange, meaning this is the right hand side of the bicycle. Bicycle is going forward that way, away from the camera, so the spoke is broken or is missing from this left hand side of the hub's flange. So that's reason one. And reason two, this is a Shimano 105 cassette set with 28 tooth sprocket as the biggest one on it, and given the flange to flange distance here on my hub, I can just push the spoke through the left hand side flange here and it's just gonna come off very easily. I moved this plastic trim out of the way here down to the height of the biggest sprocket teeth here, and it's just gonna come through, and it's very easy to place this spoke. Like I said, 3 minutes to lace it in. So that's why I'm not going to remove this cassette set, but you might have to if you have 34 teeth as a biggest sprocket or whatever else and it's in the way, and if you can't possibly lace it through without severely bending the spoke, then you're gonna have to pull off the cassette. Cassettes mount differently, and whether you can afford that tool or you have the skill, or maybe you can ask a friendly bicycle mechanic, whatever, to get it done for minimal charge for you. That's those are some of the options that happen. So let's get started. Before we take apart anything, why bother with a spoke replacement? There are two kinds of scenarios and two different answers for that. You may or may not need to replace a missing spoke. You might be able to operate a bicycle perfectly fine without any further damage to the wheel if one spoke is missing, if you are riding at a really sedentary pace, low speeds, grandfatherly pace, on well-paved roads, or wearing flip-flops, so it's like a jogging pace, or riding on a beach or something like that, and there are no significant impact loads on the wheel. You just go with the terrain, slowly rolling whatever over the imperfections or unevenness of the surface, and that is it. In that scenario, you really don't have to bother if you have one spoke missing because somebody put a foot through it or whatever else happened to it and one broke. Don't worry about it. The wheel will be fine for years to come. However, scenario number two, if you ride at higher speeds, not at this sedentary grandfatherly pace, high speeds in road riding, commuter riding, gravel bike, cyclocross or mountain biking, where shock loads are placed on the wheel as the wheel rolls, impacts uneven surfaces, potholes or rocks along its way, the shock loads need to be distributed with all of the spokes in place. So if you have any of the spokes missing, it's like you have 200 and something bones in your body. If you miss one or two are broken or screwed or bolted together, you'll be fine, but you won't be able to do high-speed tumbling and gymnastics and that kind of stuff if some of your bones are missing, okay? It's something like that. You need the loads evenly distributed on the wheel. So depending on the direction of the shock load, if you have one spoke missing and high-speed shock loads need to be dealt with the wheel, then adjacent ones might be overloaded, or different spokes might break elsewhere in the wheel if you have just one missing. Okay, so it's gonna cause an uneven distribution of load, pull or push or whatever direction. Not necessarily, these adjacent ones are not necessarily the ones that are gonna be broken next. So that's high-speed riding. Okay, so that's why bother? That's why you need even distribution of all of the loads, of the rider, of the luggage, whatever load you're carrying, and most importantly the shock loads, and that comes from the speed of riding. Okay, so that's that. Let's see what before I show you what was done so far, this spoke is actually broken. Spokes fail at typically two places. They might occasionally fail like mid-span or whatever, so with the broken end sticking out from the wheel and then it's obvious that it's broken, but that's really, really rare. It can happen if a rock goes through it sideways or a twig or whatever. But most spokes just fail here at this point of severe bending, right here at this 90-degree corner at the bottom end of the spoke, or like in this case, this failed here at the threaded section. It's about a centimeter, that's about a half an inch shorter than it should be. This failed just within the spoke nipple. So if I wasn't checking it, and this is all I saw, if I wasn't checking it for looseness, I wouldn't have caught it. And I check my wheels because I ride at high speeds, between 30 and 40 kilometers an hour in commuting or so. And okay, huffing and puffing up the hill, I'm down to 10. But that's about, you get the idea. Potholes, everything is being hit at high speed typically. And this is all that was indicating that the spoke was broken. So every 3 or so days, whatever, whenever I'm checking the chain and lubricating the chain, I check the wheels, I check the spokes. So I really didn't ride more than 3 days with a broken spoke in it. So that's all I saw. And just for contrast, here is an intact one. And if I match up the lengths of the threaded bits there, you can see that this is about half an inch or about 1 centimeter longer. So that's the new one, and it has its own spoke nipple that's intact, because the broken bit, of course, is inside this old spoke nipple, so you can't see through it. It's just inside. Okay, now let's see what was done so far with the wheel. Of course, the wheel had to be removed from the frame, and bicycle is upside down. I have a quick hub or a quick axle through the hub, which allows just removing the wheel with a simple cam lever action, no tools needed. On your hub you might find two 50mm nuts that need, two wrenches need to be rotated in different directions or opposing directions to take the wheel out of the frame. Right after that, I had to remove the tires, the tube, there they are together, the tire, the tube, and the rim tape. And of course I had to wash everything, so it takes me about an hour just to get to this 3 minutes of spoke replacement or spoke mounting. So I took good care of my rim tape. It's not super expensive, but I cleaned it and brushed it both sides with a nail brush, but why not? Because I like it clean and not ripping it and tearing it. I also checked out the rim on the wheel once this was done, especially here around the hole where it's reinforced with a grommet, but it was also checked out really well to make sure that there are no cracks in the rim in the first place, because there's no it's really unsafe to use a cracked rim, okay, especially at high speeds, like I said. So with that one done, next thing I needed to remove was, on this particular wheel, was this brake rotor, which mounts with 6 bolts. The bolts are all thread locked in place with blue thread lock compound, and they needed a Torx 25 wrench like this kind there, T25 on it, okay, and they need to be torqued to specifications when they are tightened. There it says 6.2, let me just do this so you can read it. there, 6.2 Newton meters of torque there, and they need to be tightened in also in a direction indicated, or a directional pattern indicated, like so. And there, 6.2 Newton meters is 55 inch-pounds. So you can of course eyeball all this, and you can remove your tires and tire and your tube with just a screwdriver. But of course there's a safer alternative, proper tire levers, cost you $1 or whatever in your market. And likewise you can just eyeball the tightening torque on the brake rotor bolts, but because this is a safety item, I really strongly recommend that this be tightened to specifications with a proper tool, a small enough or suitably calibrated torque wrench that's calibrated in Newton meters. Here it says Newton meters, and you can see the numbers on it. There's 4, there's 8, and this side you can see 6, 10, 14, whatever, and you can see decimal 0.8, 0.4 and 0, and between 0 and 0.4 I'm sure there's a 0.2, so 6.2 can be set with this properly. Okay, or again you can just eyeball it in a pinch, because having a wheel back together with all of its spokes is, I'm not saying it's more important than your brake safety, but your wheel will be better off with an extra spoke, even if it's just approximately not assembled, approximately tightened, you know. That can be done, you know, once you're down the mountain or whatever. Okay, I don't know why you would need to replace a spoke up on a mountain, but so if you don't have the wrench or the proper wrench with you because it breaks somewhere in the middle of nowhere, but you do have a spoke, by some miraculous whatever providence, the spoke needs to be its correct length, then you can still get it done. It's still worthwhile to get it done, even if your tightening specifications are just estimated to some degree. Okay, that's all I'm saying. Of course, the best way is the proper way, with the correct wrench and the correct tightening torque. End of story, no questions. Okay, let's get going. Now that the rim tape, the tube and tire are out of the way, the rim is checked out, and the brake has been removed, or the brake rotor has been removed, placing the spoke in is very straightforward here. You can see this on the, this is the left hand side flange here, that every second spoke is placed in differently, meaning that, for example, this spoke here is being let's see, okay, this one here, there, okay, there's my finger placement. Okay, this spoke here you can see is coming out of the hub flange this way, so it went in through this side because the button end ends up on the inside of the hub here, so it came out here and took a turn and ended up that way. Here you can see the opposite example of it. You can see a button end, so it went in from the outside, came in on the inside, and went and was laced in this way. So given this hole here, it is also obvious that because this is between two spokes that are both started from the inside here in this direction, come out on the outside and get placed that way, this spoke here needs to start from the outside and then go in. Let me just take off the spoke nipple off it and put it through there. So this is the direction this needs to go, through the left hand side hub flange. Now at this point, of course, we hit this plastic guard, or we hit the sprockets on the opposite side. Also, the spoke needs to come up somehow in this space here, where it can be bent, but not permanently bent, but it can be flexed and worked, because it needs to go forward here into this position roughly. So instead of pushing it through here, just angle it a little bit and go for this bigger space here. So far so good. Now we're still hitting this plastic guard, and if you have different sprockets, bigger sprockets, like I said, you're gonna need to pull off the whole cassette set. In this case, I can almost hit the gap between two sprocket teeth there if this plastic guard wasn't in the way, and it is okay at this point to just flex a little bit on this spoke. Just bend it ever so gently. Now, how much bending can you get away with, and how much bending is okay, it's going to be up for discussion in terms of metallurgy in a sec. But there, just to get it started, I'll show you the direction. You can see it's bent or flexed up. It's got a little bit of an angle on it, and at this point, to make it easier, I'm going to protect the threaded end here of the spoke, and I'm going to put the spoke nipple on it. I can pull by the spoke nipple, and I can push on the bent end just like so. It doesn't need a whole lot of excessive force. It comes through there really easily there with minimal amount of forcing. Of course, if you want to, you can grab a pair of pliers, maybe tap it gently. Absolutely no hammering, okay? Rather work with the spoke, bend it a little bit, angle it, but not bend it permanently, just flex it a little bit so that it springs back to straight. Or if we look into this one, let's see, or almost perfectly straight. You can see this one got permanently bent. Now, is this a garbage? No, it's not a piece of garbage now, and I'm going to explain why. Because we're not done placing it in, and with the spoke nipple in place on it, fully on it, so it's the spoke is as short as it can get, but I don't want to scratch the rim, the finish on the rim, with the protruding threaded end of the nipple of the spoke. That's why I put the spoke nipple on it. So this spoke here needs further bending, so even more severe bending than it was subject to when it went from flange to flange. And this is how this bending looks like. It needs to be going somehow in this direction, just about there. So now it's in place. So let's look at the geometry here. We went in from the outside, and that's how we ended up with this shiny button there. And on every spoke that goes in from the outside there, you can see as it comes through, it crisscrosses the spokes that go in from the inside. It crisscrosses these ones. You can see there's a, say, 2-3 millimeter, like an eighth of an inch or so gap right here where my index finger is. So where they crisscross here, really close to the hub's flange, there is this gap between the two of them. I don't know if you can really see it really well. It's kind of there. You can see there is a gap there between the two of them. Okay, so that's exactly the condition that I try to achieve when I put in this replacement spoke. Thereabouts, if you look at it, there is the gap. Okay, so it's going underneath. So this one is laced in from the outside, this one's laced in from the inside, and they crisscross the same way with a gap between the two of them, so there is no excessive bending on the new spoke or on any of them that are in the wheel. For the next intersection, the new spoke needs to be crisscrossing just like this over on top of the other one. So you can see the old spokes, that all of them or any of them that are laced in from the outside, first they go under and then they go over and on top of the existing spokes. Okay, so that's how this needs to go as well. And right about in this position here where the reflector ends, this is where the hole is in the rim. And I'm going to take off the spoke nipple, and I'm really not concerned that the spoke is slightly bent, and I'm going to explain this in terms of manufacturing in just a sec. I'm just going to put the spoke nipple in, it comes through the rim, maybe put a flat tip screwdriver on it that fits the hole in the rim, and at this point the spoke needs more bending and flexing to line up the threaded part with the spoke nipple, so it's not cross-threaded, but two of them catch and work, and it needs a little bit of fiddling and a little bit of a little bit of toying with here. Alright, so let's get back to bending the spoke. What's the deal with that? In order to manufacture this spoke, the wire from which it's manufactured is first off not cut to length, and secondly is not this diameter. They purchase stainless steel wire or steel, low carbon steel wire or aluminum wire, mild steel and very mild, soft, malleable aluminum that's on a large reel or spool. And then they pull off from that reel, and it's a big diameter, and they pull it through a series of dies where they arrive finally, as the metal is being pulled and stretched, they arrive to this spoke diameter that the whatever manufacturer, usually there's a manufacturer's stamp like a letter on the button end of this one. This one has a letter M. I don't know if you can see this black lowercase letter M on it, as in Mike. So the manufacturer arrives to this spoke diameter after pulling or drawing the spoke through a series of dies. As the spoke is being worked on and is getting thinner and thinner, it hardens. This is called work hardening. The same work hardening happens with any piece of tie wire that, and I have such a piece of tie wire here. This is an electrical, so it's a piece of copper. All metals work the same way, including mercury, which is liquid at room temperature, but once it gets solid it works the same way. So if you bend it repeatedly back and forth, of course after a while it will work harden, and once it's work hardened it's gonna snap. So bending the spoke just a little bit is not gonna work harden it just once in order to place it in, either from hop flange to hop flange, or while it's being laced in with the ins and outs of coming around the spokes and trying to avoid scratching the rim with it. Some bending is unavoidable, some flexing is unavoidable, and some of this bend that gets permanently placed in it, but just before you tighten, and the tightening will straighten the spoke, it's not a big deal, and it's not gonna cause a huge amount of work hardening in it. Okay, now at the place of manufacture, what the manufacturer does, and this is what the difference is between premium spoke and good quality spoke and whatever piece of garbage spoke. One is it made of foundry sludge in the first place, so the quality of metal that goes into it, and second, what it gets done with it as it's being pulled through the dies. So because it work hardens, it has to go through annealing. Annealing is done with a flame where the metal is heated up, but not molten, not made, you know, not dripping, just heated up to a certain annealing temperature where the internal stresses that resulted in pulling this through a series of dies and straightening it, because it's initially on a reel. So to remove these internal stresses, that's why this annealing is necessary, and it's done at high temperature. I don't know, 400 degrees Celsius, 600, there's 900 degree annealing. That still doesn't melt the steel either. And so there can be full anneal or a process anneal or just stress relieving, depending on what they want to do with it and how many dies this needs to go through to arrive to its final diameter. There can be multiple stages of annealing done to the spoke. There is also a final annealing, because this needs to be mild and flexible so it doesn't break in normal use like a piece of tie wire. So it needs to be mild in order to take this final blow to it, this severe bending. This is where spokes fail anyhow, and that's due to work hardening. As the spoke is being bent here, especially on the outside of the turn, it is being work hardened. That last corner there needs to be also annealed and the stresses relieved from the metal before this can be used as a spoke. The same happens here at the threaded end. The thread pattern is rolled between, like so, between two rolling dies. The metal is deformed and the thread is placed on the spoke material now, and of course it's cut to length at one point, but cutting it to length doesn't, or it's a simple shearing process and it doesn't really involve work hardening, but bending does, and thread rolling does, and drawing through dies does involve severe amount of work hardening. So bending it a little bit to put it in the wheel is nowhere near the same amount of bending. Okay, you can bend this spoke really questionably seriously, and it still either springs out straight or stays bent, but it's still nowhere near as work hardened as the corner is. Now, like I said, this corner gets through annealing, and if you bend it and straighten it, it won't be annealed. It will be just straightened. So as much as you can, don't bend the spoke, but if you bend it a wee bit, it's not gonna be thrashed just because it doesn't amount to a serious enough work hardening. Okay, so that's the story with metallurgy and spoke manufacturing. Now, the spokes are also subject to not bending, but something that's almost like bending, and results in spoke failure, and it's similar to bending a piece of tie wire back and forth. And this is how it goes, and that's why the last step of tensioning the spoke once it's in place is really important. So when the spoke is in a 6 o'clock position and the hub is pushing down on it with all the load of the rider and whatever else, the spoke is being buckled. You can envision it that the compressive load on it is making it buckle. It's not going to actually buckle, but that's the direction of the forces. As it rotates up to the 12 o'clock position here, as if it was on a clock face, then the hub, the weight of everything is pulling down on it. The spoke, the forces on the spoke become tensile forces, or the spoke is going to be in tension, in pull. Okay, so it goes from pull, the load is pulled on it, goes down to 6 o'clock position, to fully buckling and compressive forces. And in the 9 o'clock and 3 o'clock position here, it's halfway in between. So as it goes through fully up, fully down, 12 o'clock, 6 o'clock, full tension, full compression, full tension, full compression, the spoke is effectively goes through the same directional changes of the loads as the piece of tie wire goes through when the direction of the bend changes on it from left to right, from left to right. So eventually, even the best tension spokes are subject to this cyclic loading, and that has nothing to do with the actual bicycling, but this back and forth cycling that changes from compressive to tensile loads, and that eventually fatigues the metal. The properly annealed, properly manufactured spokes that don't get bent too much while placing them in the wheel will last a lot longer, because this loading on it will fatigue them a lot later. That's why you might want to invest your money in a proper tool such as a spoke tension meter. It has its own set of instructions for stainless steel, low carbon steel, or aluminum spokes, depending on the wheel size. The spokes should be tensioned in a way that they are all approximately plus or minus 10%, whatever, are all tensioned to the same amount, and adjacent spokes are also tensioned to approximately the same amount. So that's also what's involved. By the time you're done mounting everything with thread lock and tightening it with the torque wrench and tensioning the spokes and then truing the wheel to make sure that it actually tracks dead straight, it's gonna be, the 3-minute spoke replacement will be closer to an hour and a half easily. So I know it's a long video, thank you very much for watching, but I did want to explain this about metallurgy and the geometry of spoke lacing. Like I said, thank you very much for watching. You have yourself a good day. You be safe out there.